Okay, today we're going to start on hypothesis testing. We're finally going to get into this area of inferential statistics. We're going to be bringing together all that we've learned so far in terms of our descriptive statistics, like our central tendency and spread, i.e. mean and standard deviation, our estimates of precision, our standard error of the means, and our 95% confidence intervals, and probability that we've learned about as well. So we're going to be bringing this all together to find out how can I make an inference, and that's why it's called inferential statistics, about whether my hypothesis has support for it or not in my data. So we're going to learn how to do this in a very general way. And what I mean by that is I'm going to show you how you would do it as if you could make your own sampling distributions, because we need sampling distributions, just like we needed it for our 95% confidence intervals as an estimate of precision, but we're going to be using these as a way to make probability statements. So I'm going to show it like that. Then we'll transition into using theoretical sampling distributions, which is actually what we're going to be doing when we do inferential statistics. Okay, scientific hypotheses. We've talked about them and we've practiced a little bit, but let's really start to understand what we mean, okay? We're always trying to make a statement about, hey, if I do this, this might happen, or this might be the effect of that, okay? So here's an example we're going to work through as our general way of doing hypothesis testing. Polio vaccine and preventing polio infection in children, okay? The cause, of course, polio vaccine, and what we hope to see as an effect is reduced infection rate in children. So we want to make our if-then statement for this scientific hypothesis. And of course, we must, any good hypothesis has a prediction within it, and it's testable. Okay, so we have to have a way to refute or confirm, and we're going to get really used to this idea of support for or not support for. Okay, but here's our if-then statement. If polio vaccine is effective, then vaccinated children will get polio less frequently than unvaccinated children. We see lots of good things in that statement. What we're going to be testing, what we expect to happen when we test, and even we're getting a hint of how we're going to test it. We're going to have vaccinated and unvaccinated kids. When we come up with a research question and we're designing our experimental design and thinking about our hypothesis, we really want to think about what are these possible outcomes I might be looking for, because what would support my hypothesis and what wouldn't, right? The only way I would have support for my hypothesis is if fewer polio cases occur in kids that receive the vaccination. If I see no difference between vaccinated and unvaccinated kids, or more polio cases in vaccinated versus unvaccinated, then that is not going to support my hypothesis. So we know about the scientific hypothesis because it's really the thing that's a little more intuitive to us, right? We might, even more intuitive than that is, of course, our research question. But then we come up with a scientific hypothesis about what we think is going on. It turns out, though, that we have to broaden what we think about in terms of how we define hypotheses, because we're going to see three different types. We're going to see a scientific, a statistical, and a statistical null hypothesis. Okay, so this is going to be important. So our scientific hypothesis, like we said, it should reduce polio infection if they receive the vaccine. A statistical hypothesis would say there is no difference in polio infection rates between vaccinated and unvaccinated. And this really is our statistical null hypothesis, the hypothesis of no effect. Let's keep looking at it. Here's some examples of scientific, null, and alternative hypothesis, okay? And what becomes our statistical test hypothesis, the one that we're going to use our data to derive support or not support for, is around that null. Hang on to that. We'll keep building. Let's just focus on our polio example here, and you can read the other ones. Okay, our scientific, it should protect them. They should get less infection. Our statistical null, the one we're actually going to be testing for, is there's no difference between polio infection rate. Okay, our alternative hypothesis is that there will be a difference. Now, we don't know which way that's going to go, and this is going to be important in our alternatives because we're going to talk about one-tailed and two-tailed. So notice here, my alternative is there could be a difference, and I don't know which way it's going to go. We should also get used to using symbolic representation. Okay, again, I'm going to focus on the polio example. Okay, our scientific still in word format, and of course, if we're being really good, in the if-then format. Our symbolic representation for the null is H sub 0 or H sub O. Okay, and mu. We use mu here. You could also use X bar, Y bar. Mu saying that, of course, we're doing an estimate of mu when we take a sample, and so really we get that mean from our sample data, or X bar or Y bar. So, but we're using mu here to indicate that we're trying to say something about the population from our sample. But if you replace mu with X bar or Y bar, I'd be fine with that. So we have basically the mean for polio infection rate of the vaccinated children is equal to the mean polio infection rate for kids unvaccinated who serve as the control. Okay, an alternative way to say that mathematically, same thing. The mean polio infection rate for vaccinated children minus the mean polio infection rate for control equals 0. Okay, so really understand what that mean is talking about. And that was intimated in what we were doing in our scientific hypothesis. Okay, that we were looking really as an outcome variable, polio infection rate. Okay, so the alternative then simply is they're not equal, or they don't equal 0. I don't know where they're going to be, but they're just not going to be the same, or they're not, and thus they're not going to equal 0. So statistical hypothesis testing really is this idea that we assign a probability, okay, to our experimental results. And that probability is the idea that it's a probability of what would happen under random chance alone, okay? Random chance. And I know I've talked about the rare event rule, right? And so we're going to say that if a probability is very low, that it probably isn't random chance. It might be something else, okay? So from the statistical hypothesis test, we get to draw a conclusion, right? We can compare means all day and say this one's bigger than the other one, which is important. But we want to have some evidence to say, hey, I really feel like maybe something's really happening, or not. Okay, so in the Salk vaccine, if we find evidence that the polio rates in vaccinated kids are not the same, but instead lower, right, then we'll conclude that we have data that supports the idea that the polio vaccine worked. And that's eventually what we want to get to. Or not support it, because if it doesn't support it, that's still a result. Okay, so here's Jonas Salk's actual vaccine trial done in U.S. and Canada in 1954, over 400,000 children whose parents allowed them to be in the study. And they received either the vaccine or a placebo shot. And it was blind to the children and parents. Okay, so not double-blinded, just single-blind. Okay, here are the results. Out of those 200,000 kids that received the vaccine, okay, 0.16% of vaccinated kids got polio. Out of the 200,000 kids who did not get the vaccine, but the placebo sugar water, 0.5% got polio. So right now we're looking at that and we say, okay, the rate of infection in unvaccinated kids was higher than the vaccinated. All right, we're in the right direction. Is it real? Okay, is this just random sampling error, right? We know that if we did this test again, the chance that we would get the same means in each group is low. We're not going to get the same means. We're going to get a slightly different result, hopefully in the same direction, but it might not be. And so that's what we're trying to find out. Is it just the fact that I, for whatever reason, got this subset of kids in this infection rate? Of course, there's confounding variables that I hope through random selection that those were equal in the two groups, right? We don't know how often they came in contact with infected people, things of that nature. So by random sampling, we just hope we even that out, but we want to make sure that what we see here, that lower infection rate, isn't real. So we're going to do hypothesis testing, and we're going to be testing our statistical null, okay, our null. What we're going to test, okay, is if the vaccine had no effect, what's the likelihood, what's the probability that we got that difference that we saw between the vaccinated and unvaccinated kids, okay? So we're going to create a sampling distribution, pretend. Okay, so I'm going to take a population of kids that large, right, in which I didn't do anything, right, and they had a rate among all these kids of 0.0365% with polio, okay, and then among 400,000 kids. I select two random samples, 200,000 children in each, and so it's a random shuffle. And then I look at the mean of infection rate between those two kids, right? What would you expect? You would expect, I didn't do anything to these kids, so you would expect the polio rate, right, to be the same in the two groups that I just randomly put them in, right? And should be around 0.0365%, right? So I'm going to create a sampling distribution as if I did this a million times. And I'm going to create this. So what you have here is a null sampling distribution. In other words, I'm saying if I took those means of rates of infection between these randomly selected two groups, and I did it a million times, and I minused it, and I took the polio infection rate from the control, and I'm putting that in quotes, and the treatment, on average, you'd expect to be 0 because it should be around 0.0365% in both groups. So if that's true, this null distribution, this distribution that should happen under random chance alone, should center on 0, and it does. And of course, notice it's a probability density now because I'm talking about a sampling distribution. I did this a million times, got the two group means of infection rates, subtracted them, and plotted how many times I got that difference. So that's a null sampling distribution. I don't really create these in the real world, and so, but I'm pretending here this is what I'm doing. Okay, so what's the probability of what we got in the real study versus what we should see in our null sampling distribution? Where does this difference fall on my null sampling distribution, and what's the probability of where it falls? That's what I'm asking. Okay, so the difference that Salk got between these two groups is 0.041%. So remember, 0.05% for the unvaccinated minus the 0.016% for the vaccinated kids. So that was the real experimental data. Back to my null distribution. It is way off to the right if that curve, okay? Do you think the probability is low over there? Well, indeed it is. I'm going to use a relative frequency approximation here for my probability. And so I found that in that null sampling distribution, 20 times 20 times, I found random differences as big or bigger than Salk's actual result. Okay, so I put that 20 over the million, and that's my probability, 0.0002. Okay, so it's very low. And remember, rare event rule. If the probability is very low, it's probably not likely that we saw this by chance. Okay, if our probability was somewhere in the tallest part of that curve, it's going to be very large, something like 0.5 or 0.7 or even 0.9 if it takes up almost the whole curve. So and that's when we say, hey, that's probably chance. But when it's way off to one tail or the other, or both as we'll see, then we're going to say it's not likely due to chance. So we conclude we have evidence to support that it worked. Okay, we're taking a very small chance of being wrong, a probability of 0.00002 that we're wrong. Okay, so that's why we never prove anything, but we have evidence to suggest, evidence to support that it worked. So here's our general statistical null hypothesis testing procedure. We hypothesize that any difference observed are due to random chance. That's the null. Okay, no difference. We choose a statistical test. In this case, it was the difference in those mean polio infection rates. Okay, and that became our test statistic. And our test statistic, basically, to get our p-value was how many times did we get a difference that big or bigger. And if the probability of observing the experimental result by random chance is small, rare event, the result is statistically significant. So we reject. We don't have support for our null hypothesis. Instead, we have support for our alternative hypothesis. We could be wrong, right? We always are acknowledged of that. We never have p-values of 0 or 1, but we're looking for what we call rare event to give us support for our alternative. Okay, so this was a general way to do it, okay? And so I said we don't create null sampling distributions. So we're going to move into this idea of using theoretical distributions, sampling distributions, to get probabilities. And these are null theoretical sampling distributions. All right, there are several different methods, okay? I just showed you the p-value method. And it actually really goes hand in hand what's called the traditional method, rejecting the null if a test statistic falls within some critical region. We'll look at this more, okay? So this won't be the last time we talk about it, but just understand that it's out there. We'll also see confidence intervals, and there's a lot of mathematical connection between these two, but we'll see that confidence intervals can tell us a couple things, but we can also reject a claim that a population parameter has a value that is not included in the confidence interval. Okay, so if 0's in our confidence interval for a difference, and we can make confidence intervals for a difference, then we're going to say it's not different from 0. Don't worry, we're going to see that again. Okay, we'll also see how if we make confidence intervals just around our samples, for two groups, when they don't overlap, most of the time we're going to see that we're going to get a low p-value and a test statistic that falls within the critical region, leading us to reject our null in support of our alternative. Okay, so if you're asking, why am I testing a null hypothesis instead of my alternative or my scientific? I'm really after that. Well, here's the problem. We don't know what an alternative value to test for is. The only value that we know that we can test for in our statistical hypothesis testing is 0, null, no difference. So there's 1, right? We'll see even in sometimes our null value might not be 0. It's the most common, but we can define it, and it is an exact value. Whereas in an alternative, it can be anything outside of that null. We're not sure where it's going to be. So there's an infinite number of them. And so that's why we use the null. The null is an exact value, usually 0, but not always. And that's something we can really specifically test against to see how far away we are in our null sampling distribution from our null value. And the farther we get, the probability goes down, and then we think it's not by chance alone. Okay, one tail or two. So we're really going to talk about this more and more. But when I was looking at the Salk vaccine example, we looked at differences that were bigger than what was found in the study. And so what I really was showing you was a one-tailed approach, just that right tail we were looking at and the probability over there. But remember in that alternative hypothesis where I was saying there will be a difference, but we don't know which way it's going to go? And that's because we're cognizant that for most of what we're going to be doing, well, for everything in this class, but I'll tell you why as we move forward, we're going to be doing a two-tailed. In other words, we don't know if the probability will be in the right or the left tail, so we're going to include both.